Okay, can you see my screen?
Yes, sir.
So yesterday we were learning about these joints, right? Like how do we, what is it, what are these joints, and what are their properties, right? How do we get the orientation of those joints? And then we talked about, how do we get the cohesion and friction of these joints using our direct shear testing machine. All right, then we talked that we have big specimen where, if we have some bigger samples to take, then we have these huge casting machine, and then we learned that we can do the this joint testing in the site also. And we were talking like how this stress strain curve or the shear stress shear displacement curve looks like for this test. Like the last thing which was remaining is, there is something called a Barton Bandis joint strength model, but we are going to skip this one, right? If today if time permits, I'll come back to this part again. Okay, so now next thing which is very important when we do the design of an underground excavation is the in situ stress. Okay, so just a second. Yeah. So, like let's say we first from our previous classes we knew that what is the property of the rock, right? Like if some boundary condition is applied to a rock sample, how it fails, right? Whether it can, what is the load it can take, right? So that is what we now know for different boundary condition like direct tension, then UCS, triaxial, and also for the joints. So next thing which is very important when we go for design of this underground excavation is what is the in situ stress. Let's say we are creating this tunnel here at a depth of, let's say, 250-meter with same kind of rock properties. So the rock here is, for example, let's say UCS of 150 MPa, right? But if the same tunnel, same diameter tunnel is depth, like dug some, let's take a break here. So let's dug at a depth of, let's say, 1.5 kilometer. So these are two different cases, right? And the difference is due to the in situ stress, something called in situ stress. So what is this in situ stress? A mining student, anybody? And why we call it in situ stress?
So the stress that is present in situ condition, like no changes are done in that.
So before excavation, right? Like
Yes.
we can say before excavation. So what does this mean is, like let's say before excavation, the stresses, the vertical stress here is, let's say 18.6 MPa. So when we make some excavation, the stress around this opening that changes. So maybe around here in this zone, the stress will go up to, let's say, 32 MPa. Okay, but same depth, if you change the excavation geometry, this will no more be 32 MPa. It will be 56 MPa. Okay, the new stress, or maybe because of the excavation at the same depth, if you are making the excavation, the stress changes, right? So this is due to the in situ stress plus your the change in stress due to your excavation. Okay, is this clear? So there are three things basically. One is what is the rock properties. Second one is what is the in situ stress. And third one is what is the excavation geometry. Okay, so we combine these three and then we do the design. Okay, so this is a concept. And anybody has any question? Okay, so this is something called a geological section. So anybody who doesn't understand what is this section is geological section, or anyone? What is this geological section means? What does this mean? Anyone? You had your engineering drawing course, right? In your first year. Yes, sir. So this is the same section, right? Let's say you have, from the top, from the satellite, you are looking at ground and maybe some, some geological features are there, right? So if you take a section here, uh, right, and see, then how it looks like is your is like a vertical section, right? So maybe this is a mountain. Okay, and you are just cutting through that mountain, a vertical section, and this is how it looks like. And this different color here, they tells us what are the different type of rock. Maybe for this one, oligocene, maybe the geology student they can say what kind of rock is this, right? I mean the pink one is different, this blue one is different, green one is different, right? So it's like that. So when you excavate something, you know. We cross through, let's say a tunnel is dug through all the way from here to here. Okay, so if you see here, if you have, let's say, take few points, one, maybe two, right, or maybe somewhere three here, maybe five here. So one, two, three, four, and five. So if you see here, maybe the point three is below the mountain, right? And it has maximum possible cover, like in this section. And maybe this four is the lowest cover where the tunnel passes through, right? So maybe this is around 750 meter, let's say, and this can be, let's say, 460 meter. So even if like is the same horizontal tunnel, what is the stress condition that you will meet at point 4 is different than this is than point 3, and which will be different in point uh, point 1, right? Or maybe point 2 will be different. So and the thing is, maybe it is at point 3 we have different type of rocks where we are doing the design, right? Maybe this is falling on this pink thing here and the green thing here and passing through this pink again, right? So is this clear? Anybody has any question up to here? Can anybody tell, like, if you can listen, or
Yes, sir, we can listen. No question.
Okay, okay. Because like sometimes what happens, the internet goes, right, and you don't know that the students are listening or not. So it's you will be just talking and then but nobody is there in the front, right? So I will request you to please respond.
Yes, sir.
Okay. So this is what I was saying, at different location that stresses will be different. Now this figure here actually shows the plot between, how this vertical stress, because if you see this is a ground surface and your project is somewhere here, then there are two things actually. One is your vertical stress, which call it sigma v, which is acting in vertical direction. So if you put something here, what is the stress is going to apply in vertical direction is your vertical stress. Okay, and what is the stress is going to apply in this direction is your horizontal stress. Maybe this is capital horizontal stress. What does this mean? Is this is the major or horizontal stress, you can say. Okay, so this is our vertical stress. So another stress which is perpendicular to this sigma h direction is your called sigma small h. Okay, this is a minor horizontal stress. Okay, so maybe something we are skipping here is, we have 6 components of stresses, but we can, bring out the 6 component to 3 principal stresses. You please, those students who doesn't know about this 6 component of this stresses, please look into, go to Google and or maybe see some books. You'll be learning about. You can easily find out this thing. Okay, we are not discussing because like if you discuss everything, it will be just another rock mechanics class, right? So we are not going to do that. So we have basically, you just assume that we have 3 principal stresses, one in like in mutually perpendicular directions. So this is our, let's say, x, this is our y, and let's say this is our z direction, right? So this is minus z direction. So the stresses in any point can be, divided in or maybe can be made in 3 principal stresses. We call it sigma 1, sigma 2, and sigma 3. So where this just a second, where this your sigma 1 is your major principal stress, sigma 2 is your minor principal stress, and sigma 3 is your, sorry, this is intermediate principal stress, and this is your minor principal stress. Okay, so did you understand about these things? So at any point, when you do the or maybe start the project, at any point you have 3 different stresses. One we consider is vertical stress, and 2 of the stresses in horizontal direction, right? So either this can be your sigma 1, this, or maybe sigma 2, or can be sigma 3, depends at different conditions, right? So this will be one of the sigma 1, sigma 2, and sigma 3. This is sigma 1, sigma 2, and sigma 3. Anybody who did not understand, because I'm skipping so many things here. So if you have any question, please let me know. Otherwise, it will be difficult for you to understand, especially the geology students. Anybody has a question?
Sir, no.
Okay. Can I just ask, like, those don't have any question, can you please raise your hand? I just want to see how many of you guys are, attended, really attending these classes. Please be quick, we don't have so much time. So I just want to add something here. These questions in your exams will be very conceptual. Okay, so if you don't understand, then it will be difficult for you to answer those. So please let me know. See, we have still so many students. They are, I don't know what they are doing. Vishal, are you there? Or Sai?
Yes, sir.
So you have any questions, Sai?
No, sir.
No. So then why you are not putting your hand
Oh,
up, or you did
I
not
actually I didn't
understand?
understand the question, sir.
Yeah. So
The
this is what I
network
was saying. Few
there
of
was
you guys, you are not being attentive, like, or maybe you know everything. So this is one of the two things. So do you understand what is this major principle, minor principle, and intermediate principle stress? Okay, let me quickly, recap. So let's at a depth of Z, you are constructing something. Either you have a mining project, civil project, or petroleum project, whatever project you have. So there you have three component of stress. One is in the vertical direction, two are in the horizontal direction, and they are mutually perpendicular to each other. Okay, and one of them can be your major principal stress, another can be your minor principal stress, and third can be your intermediate principal stress. But we don't know which is what. Okay, so this is the story, right? And we really need these values when we go for design of any underground structures, right? Because whether it's going to fail or not, that depends upon our in situ stress. Okay, so if you see this figure here, this is from Hook and Brown. They have compiled this figure in 1981, and what they did was, they tested, or maybe that they performed this in situ stress test, something called stress test results. So they compiled everything and put it in a figure, right? Like, one in this direction is the depth Z, and this is your vertical stress. So what does this mean is they put from all around the world, from the globe, all the places. So wherever some data is published, like in different location in the world, so they took those data and put it in this figure, right? Put it in an Excel file. So this, you can see, this is Australia, this is Canada, USA, South Africa, Scandinavia, and other regions. So he put all these data in this plot. So, and let's say this point here, this says at this vertical stress, or maybe this vertical depth, you have your this much vertical stress. Okay, so this much is, like, let's say at this is 650. So at the 650 meter depth, so this is your 650 meter deep, you have a vertical stress of maybe how much? Can anybody tell me? Guess what is this value here?
Maybe
Around
7.
27.
Okay, very good. 27. So you have a vertical stress of 27. So he plotted this 650 by 27 is one data point, right? So similarly, he compiled all these data points all around the world and put it in this figure. right? And he found out that this interesting, fact that it is more, all the data points lies around this line. So this is a line. This is like a line with y equal to mx plus c kind of thing. So c is 0 here, and this y. What is this y? Y is your vertical stress sigma v. Is your this 0.027 times z. So most of the places, what we do, let's say we design something, we don't calculate, like go and find out what is the vertical stress. We just assume that like let's say you have at 100-meter deep, you just calculate that my vertical stress will be 0.027 into 100 equal to your 2.7 MPa. So this is a reasonable kind of assumption. Is this clear? What is this vertical stress here and how do you calculate? So for your project, let's say is the depth is 450 meter, right? So you just multiply 450 with 0.027 and whatever this value comes, that is your vertical stress. This is what generally actually people do. Okay, so maybe there is some variation. So if your project is really, really critical, then you go and test the, test that in situ stress and get that value. Okay, but most of the cases, I don't know, like in India, and anybody does that kind of things. Maybe for nuclear waste disposal or those kind of, very critical cases, we go for these really in situ stress measurement. So we calculate using this equation, and most of the cases is we found that it's a very reasonable assumption. Is this clear, this vertical stress?
Yes, sir.
Okay. Yes. So then we have another thing which is called stress ratio. K is your stress. What does this mean? Is mean of horizontal stress divided by your vertical stress. So this is done here, 0.5. So this sigma xx, maybe this is your sigma capital H, this is sigma small h. So sigma small h plus sigma capital H divided by 2. So this is multiplied by 0.5. So this is divided by 2 divided by sigma vertical. Okay, so this is what it is done. And this result, it is very interesting here. See, so most of the cases, let's say your 1,000-meter deep is here, so it's the same thing. So it is 500-meter deep and this 1,000-meter deep. So most of the projects, like either you go for mining or this not petroleum mining or civil projects, they are within this 1,000-meter deep, most of them. But if you are going for petroleum, maybe you are talking about some 2,000, 3,000 meter from where you extract the crude oil, right? So maybe the petroleum is somewhere here. Okay, so if this is the this is the case where if you see all our projects are lying above this line, so you can see the K ratio, which is the ratio between your horizontal and vertical stress, that lies from 0.52 all the way up to 3, right, or even more than 3. Okay, so this knowing this horizontal stress is very, very important. Can anybody tell me why this is happening? Why there is a horizontal stress is more than this vertical stress for most of the cases. So sigma h equal to sigma v is this line. Okay, so but most of the data point lies in this region here. So see. So what does this mean is, let's say you have a project here. The vertical stress, what you are going to get here in this direction, is always less than your sigma capital H. But why this is? Planning students, you have already learned. Can you please tell me? Anybody? Anyone? Hey, you almost forgot. Who is here? Let's see. Who are the mining students? Can you raise your hand?
Sir, they gave us a theory, something kind like in Ice Age there was too much vertical load, but when it went away, the horizontal stress remained, but the vertical stress decreased. Something kind of that.
Yeah, this is one of the logic, right? Like that we talk, right? But all the places we don't have this ice age thing, right?
Yes, sir.
So there also this is the same case. Can anybody tell me the answer? What is happening here? Okay, let me quickly tell you. Geology students also know. Can anybody geology? Bunty, are you there? Or maybe Chinta or somebody else? Can you put your hand down, please? Chinta, are you there?
Sir, yes, sir.
So why the horizontal stresses are more?
Sir, I don't.
You don't know. Do you know earthquake?
Yes, sir.
What happens? The plates they collide, right?
Yes, sir. Plates good.
So what happens? Like let's say this is what is happening. Okay, so this is our this is this continental drift kind of thing, right? Let's say this is our Himalaya region. Okay, so the Indian plate, this is the Indian plate, and this is Asian plate, right? So the Indian plate is colliding, or maybe the hitting the Asian plate. Okay, and because of that, this mountain range is formed. So if you want to, like, because this plate and this plate, they are pushing each other. If you want to see what is the stress, let's say in this location A here, the horizontal stress will be too much, right?
Yes, sir.
Stress at A is very high. Okay,
Yes.
and this is the main reason actually why we have very high horizontal stress. So if it is near to your this plate tectonic boundaries, you get a very huge in situ stress. This is what it is shown in this figure here. So we have, I think, seven plates that we assume that major plates that our Earth is made of, and they are continuously moving. Okay, so this maybe this is our one of the plate. Let's say this is called Pacific plate. So this specific plate is moving in this direction. So this red is showing that there is tension between them. They are getting separated. So maybe it is Eurasian plate. This Pacific plate is moving away from this Eurasian plate. So that there is tension here. Okay, if it is going towards this Atlantic plate, that's why you have compression here. Okay, and this compression here is because of this compression, the stresses here at point 1 will be too high, and then it will be point 2, it will be little bit less, right? At point 3, it will be further less. Okay, so it depends how far away from this plate boundary our projects are. Okay, is this clear?
Yes,
Yes,
sir.
sir.
Okay, so where is India? Is India here? No India. Okay, no worries. So, oh yeah, India is here, right? See, the Indian plate, Indo-Australian plate is called. Indo-Australian plate is going towards, I'm sorry, the red are towards that, right? I just told it in opposite way. The red are going towards, so the whole Indian plate is going under this Eurasian plate. Okay, and that's why some few inches we are going inside the mount. The plate is itself. The India is going into, you can say, below China, right? In every year a little bit. Okay, and because of that, if you see, we have earthquake here, and if you have some project near let's say Jammu and Kashmir or some part of this, this what we call like our northeast region, then we have high value of stresses that we need to consider when we design for some, this what is called your civil or mining projects. Is this clear?
Yes, sir.
Yes, sir.
Okay, so then there is something called
Yes.
world stress map. So I took this picture from here. So there are very good people, they work, they help us. What they did is you can just quickly browse this, just to Google this, and like you can type something called world stress map in Google. Okay, so what it does is like there is a group of people, I think Germany, from Germany, they have compiled all the data and they put it like a figure, right? So they in this world map, and they have shown actually where are those locations where we have some high value of in situ stress. Okay, so see, these clearly shows, near the plate boundary, you have huge amount of stresses. And two things that you can get it from here is, like let's say, let's go to close to some place here in India. Okay, so we just talked about, the orientation of a, this kind of uh, is this orientation of an underground opening, right? So let's say you are making something. Let me take it. Okay, so let's say you want to make something here, right? And this world stress map tells us like where are those locations where you have used in situ stress and what is the direction of this in situ stress. See, this is towards the major principal stress, which is our sigma h, maybe is in this direction. Okay, so let's say you are constructing something. So the major principal stress is in this direction. This location, this direction, right? So this major principal stress direction is changing at different location. Okay, so at let's say point 1, you have point 2 and point 3. So if you are constructing something at point 1, point 2, and point 3, you can say what is the magnitude of this, horizontal stress, what is the ratio between the horizontal and vertical stress, and what is also the direction. So those two things, I can say first thing is direction of sigma h, or I can also get the second thing is the magnitude of this, the sigma h. Okay, so these two things you can get it from this world stress map. Okay, so they can like they give you some idea, but this from this point to this point it can be some maybe 900 kilometer, right? So if you have some project between here, you can just assume that okay, my direction is this direction, but if you want to construct something there, you need to really do some kind of site investigation, right? Or maybe in situ stress measurement. So like we do our geological surveys, or maybe we were talking about this site inspection kind of thing, right? Like so on top of that, we need to do this in situ stress measurement in different locations. Anybody has any question up to here?
No, sir.
Okay, it's pretty clear, right? So let's try to solve this problem. It's very simple, right? So this is, this is ground surface is here, and let's say we are constructing something at 2 kilometer plus 50 meter plus 800 meter down here, all the way down here. So can you calculate what is the initial stress? The densities are given. So this initial vertical stress is the summation of, gamma times z. Okay, so this equal to your 9.2 kilonewton per meter cube. So 9.2 into 2 kilometer, right? 2000 plus 50 into your 16, or maybe we can write 16 into 50 meter plus your rock is 800. So 24 into 800 is in kPa. Can anybody tell me what is this answer? Or can you please put your answer in your chat box so that I will know that who answered it. So whatever is this is the value. Let's say I didn't calculate it, right? Like so maybe uh, I don't know. So now the second part of this question says ask actually about horizontal stress, right? So the horizontal stress by vertical stress equal to your K. This is equal to 2.5. So if you just give it sigma V here, so that horizontal stress, which is called sigma H, let's say equal to 2.5 into uh, what is this 2.5 into your sigma V. Is this clear? Anybody has any question about this this problem or the example we are solving here?
No, sir, it's clear.
Sir, it is the
Okay.
mean of horizontal stress. Yeah.
Yeah, this is the mean of horizontal stress, but we actually ignore and sometimes, when we don't have any data, we assume that the horizontal stress is in all direction is constant. So we don't have, we just assume that sigma h equal to sigma capital H. Okay.
Okay, sir.
Yeah. Ideally, we should have, these things separately. But if we don't have that, the data, like we just assume that both are constant. Okay. So now different ways to get this in situ stress, right? Or maybe in situ stress measurement. Mostly what we do is we drill a hole, somehow go, let's say our project is somewhere here, somehow we go here and drill a hole, either from vertical or you just make a drift and drill a hole and do the test here. Okay, so there are different type of tests. We are not going to discuss about that. If you just want, you can just go through all of them. Like there are hydraulic method. One is called hydraulic fracturing method, slip fracturing method, hydraulic test on pre-existing fracture. Then we have relief method, right? So surface relief method. So we have n number of tests that those are used to get the in situ stress. Okay, so this is from MAD and Stevenson. So, and we have something called ISRM. For those who don't know what is this, ISRM is the body which takes all the decision related to rock mechanics, right? It's called International Society of Rock Mechanics. So this recommends, it's like a, these guys, they recommend us something, how the test should be done and what kind of test should be done, and many things. Okay, so if you work in the field of rock mechanics, you will be knowing about this thing. So we have this ISRM suggested method, and it actually suggests four methods. First is the flat jack method. Okay, second is the hydraulic fracturing method. The third is the USBM overcoring method, and fourth is the CSIRO overcoring method. Okay, so these are the four methods out of those all those above method, like this ISRM recommend. And the most famous or most widely used method is your hydraulic fracturing test. So we are not going to discuss about, maybe in your rock mechanics, you learned about this flat jack and the overcoring method, but we will quickly see this hydraulic fracturing test. Okay, so yeah, so hydraulic fracturing test, what is done is, like we let's say this is the location where you want to, or maybe this is the depth of your project. This is your Z, or depth of your project. This is where you want to find your in situ stress. So first thing what we do is we make a drill hole. Okay, so then what we do is we put something called packers. Okay, and expand this packer so that we isolate some kind of area in here. Okay, in between that borehole where you want to do your measurement. Okay, and then what we do, we put this pipe. Okay, this pipe here, which goes inside this borehole and into this area. Okay, so these pipes are with holes. Okay, so and these packers make this wall so tight that when we apply some fluid pressure here, so the oil comes out of these pipes, and it applies pressure all around. Okay, so when it applies all around pressure, and this packer is so so designed that it is not going to move up, so it is not going to move up, it will stay there. Okay, and you keep on increasing your pressure here, so that like there will be some kind of fracture which develops in the rock, because when this pressure becomes too high, it develops some fracture. Okay, so this fracture goes like in one plane, this whole thing will open. Okay, and this will be separated, and this will be separated. This will be, the rock will be separated. Okay, did you understand like what is happening here? Anybody who did not? So this is the concept, like how it is done. Bunty, are you there? Bunty or Chinta?
Sir, yes, sir.
So did you understand what is happening here?
Yes, sir, I understood.
So just drill a hole all the way down where you want to, do the test, isolate some area here between between these 2 points, right? You isolate this area, put a pipe here, and apply some fluid pressure, and increase that fluid pressure till this fracture that open, begins inside this drill hole. Okay, so this is what it is done. So now, if we plot this thing, or maybe before that, what happens? Let's say you take a section here, and and you are looking from the top, and so this is the circle, right? And let's assume that you are applying the in situ stress here is 100 MPa, and this is, let's say, the smaller value of this horizontal stress. This is your sigma capital H. Sigma small h is your, or maybe we don't know. Yeah, or maybe this is the major, because this is major principal stress. Sigma h capital H equal to this much, and sigma small h equal to, let's say, 12 MPa. Can anybody tell me in which direction this fracture will begin?
So can you repeat?
Like you have some in situ stress, which is sigma capital H is 100 MPa, and sigma small h is 12 MPa.
Yes, sir.
Okay, so let's
What?
make like this. So you have a plate here, right? Or A, B, C, and D. So, and you are applying some 12 MPa load from this direction all the way, and this direction is your 100 MPa. In which direction the crack will open? Can anybody tell me if I keep on increasing this pressure?
So 12.
12 direction means what?
So like the crack will develop.
So which direction? Let's say another, we have some point E and F, and
So like where the maximum stress will be there,
G,
we will crack that.
G and H. So in which line the crack will open? EF or GH?
EF.
EF. Why?
So because we can like 12 MPa will be like it is less, so in EF side the crack will
It will
develop.
be easier to push, right?
Yes, sir.
Yes. So if you see
Yeah, sir, we
this,
also saw in that Brazilian test, like 2 point load were applied and it opened in
no, it's
that
not
direction.
about that Brazilian test, but like it will be easier to crack it like this, because this magnitude is less. So if you want to push it, like it will be easier to push in this direction, right? Opposite to this. This in this direction, pushing is a little bit difficult. Okay. So I'm sorry, I'm just taking a little bit more time here. So what happens when you do a what is this called, your hydraulic fracturing test? So what happens if you plot the time versus your T? It looks like the pressure it is increased, and here the fracturing happens. So this is called PB PB. Okay, so breakdown pressure. Then once this fracture is open, this pressure suddenly goes down and reaches to a value which is your called PS, is your shutdown pressure. So then the pump is kind of, switch it off the pump so that the pressure becomes almost zero, and then you do something called a reopening of this thing. So the structure is there, and then you started your pump. So this where this pump will again reopen the fracture is equal P reopening pressure. So P RO equal to reopening pressure. So we have basically three formulas here. I'll just quickly write. I'm not explaining. Okay, based on there is something called Cauchy equation. So we have three things here: PB minus P reopening equal to. Can anybody tell me from your mining students what is PB minus P reopening? No, you don't remember. This is your tensile strength of rock, sigma T. Okay, because first thing is when you are breaking this hole, you had your tensile strength of the rock here, right? And second thing is and on the broken thing, you are reopening this. So the difference between PB and your reopening, this difference is your sigma T. You just think about that. If you have any question, just let me know. So this is the first equation we have. Second thing is, the shutdown pressure is your small sigma h. So PS equal to sigma small h, small horizontal stress. Why? Because when it is closing, this crack is closing. This is reaching towards what is the value of pressure that this crack surface is applied in this direction. Okay, that is your sigma small h value. So this PS is your sigma small h. You just try to see it. If you still have any problem, just let me know. And third thing, what we have here is called sigma h, sigma capital H, which you can find out using your PB minus 3 sigma H plus sigma T. So this is the third equation. Okay, so now what I'm going to do using this thing, I'm going to give you some problem. So where you want to calculate the in situ stress values. So this is your problem. Okay. So I'm going to share this, like this PDF with you. You please solve this thing at home. And if you have any question, let me know in our next class. Okay. So here the course questions are there. So just to repeat, we do this hydrofracturing test and we get this different value, get this plot when this motor is connected to a computer, right? Like maybe this the pump here is this hydraulic pump is connected to, let's say, computer, and in computer screen you can find out how this pressure versus time looks like, right? This plot is given in the computer screen, and once you know this like this plot, and you find out what are the different value of these things here, you can calculate what is your first thing what is your sigma small h and what is the sigma capital H. This is our target. And the vertical stress, how do you calculate it?
Okay.
Anybody? Yeah, this is gamma z, right? Or maybe you can use this formula which says 0.027 times your z. So by doing this, you can calculate what is my first principal stress, second principal stress, third principal stress, and then you can go for your design. So I request you to go through this problem. Please solve it yourself. If you have any question, we can see it in our next class. Okay, so let's stop it here. Thank you so much. Let me quickly download this thing, and I would request